Hello, and in part 2 of these short videos about circuit analysis, we'll be looking at the fundamental equations that describe the behaviour of the components in the circuit that we're trying to analyse. We've seen all of these equations before. I just wanted to revise them and make sure their application is clear in everybody's mind before we go any further. So, what equations am I talking about? Most importantly, Ohm's law covers resistors. If I have any resistor, then the change in the voltage from one side of the resistor to the other is equal to the current flowing through the resistor times the value of the resistance. We also know about voltage sources. For a voltage source, the change in the voltage from one side to the other is equal to the value of the voltage source. We've come across current sources as well. For a current source of magnitude IS, we know that the current flowing through it is equal to the magnitude of the current source IS. There are then Kirchhoff's two circuit laws. Kirchhoff's current law, saying that the total current flowing into a node, or rather the total net current flowing into a node, is zero, although I find it easier to think about that one in terms of the total current flowing into a node is equal to the total currents flowing out of a node. Sum I in equals sum I out. Then I don't have to worry about the fact that currents flowing out of a node are negative currents flowing in. And then there's Kirchhoff's voltage law. And you'll notice that on the slide, I've greyed this one out. And the reason is that if we're doing nodal analysis, we don't need it. If we were doing mesh analysis, which is the other way to do circuit analysis, we would need Kirchhoff's voltage law. But just using nodal analysis, we don't. So those are the two most important ones that we're going to be using. There's another one, of course. If we're using diodes in our circuit, we'll need to use the Shockley equation. For a diode, the change in voltage across the diode is related to the current flowing through the diode by the formula: the current is equal to the saturation current of the diode times e to the power of the charge on an electron times the difference in voltage across the diode divided by n, the ideality factor, times the Boltzmann constant, times the absolute temperature in degrees Kelvin, minus 1. It so happens that the Boltzmann constant times the absolute temperature divided by the charge on an electron works out to be about 25 millivolts at typical lab temperatures. So we usually simplify that one to change in voltage divided by ideality factor times 25 millivolts minus 1. And that's fine for typical lab temperatures. Now, the problem with all of these equations, but in particular with Ohm's law, is you have to be absolutely clear what the direction of the current is and what the difference between the voltages is, in the sense of, is it this voltage minus this one, or is it this voltage minus this one, to get the directions correct. That's probably the thing that goes wrong first for anybody who's starting off with circuit analysis. And I find the easiest way to make sure that you get that right is to write Ohm's law in the form VA minus VB equals IAB times R. The A and the B are in this order on the voltage side and the same order for the currents. And that means that the current is flowing from A to B. So if I have this resistor here, if this is node A in the circuit and this is node B in the circuit, It's often a good idea to label the nodes in the circuit like this. Then the voltage at node A would be VA. The voltage at node B would be VB. And I would write Ohm's law as it applies to my circuit here as VA minus VB equals IA to B, so a current flowing that way. IAB flows in that direction. For the voltage source and the current source, it's easier to remember which way round things go. If this was our node B, then for the voltage source here, we would have voltage at B minus voltage at A equals the voltage source, because the voltage here is bigger than the voltage here by the amount of the voltage source. For the current source, this current is in the direction from A to B, so I would just write A to B. The current from A to B is equal to the current source IS. Kirchhoff's current law will take care of itself because we've defined what direction all the currents are going in. And the Shockley equation, same issue. We've got to be clear which direction the current is flowing. So it's probably better to write it in this case as I from A to B equals the saturation current times e to the power of the voltage at A minus the voltage at B over n times 25 millivolts minus 1, with brackets around it like that. But do take care, because this is the thing that tends to go wrong. And the best way to make sure it doesn't go wrong for you is to draw out the circuit diagram, label the nodes carefully, and draw arrows to indicate which direction all of your currents are flowing in. When you do the analysis, some of these current values may turn out to be negative, which would tell you that in fact the current is flowing the other way. But while you're doing the analysis, define which direction you are treating as a positive current and stick to it. It'll get easier with some practice. Okay, in the next short video, we'll look in a bit more detail about this algorithm, the nodal analysis algorithm.